We've got more great questions this week to start us off with your curiosity. Our first one is, what is the purpose of harmonics? Is it for targeting or what? Now remember, harmonics are those signals that seem to be at higher frequencies, at multiples of the frequency that a bat will often make and that we'll see in our recordings when we have a good enough recording. And so I think inherent in this question is a little misconception that the bat can turn those on or not. Last time, we can watch our video from last time where we were looking at the harmonics of a string, and the string doesn't get to decide whether it wants to make a harmonic or not. It's something about the physics of how it's put together and how it's suspended in between its two edges. And so the same thing with the bat's vocal cords. So it turns out, though, we're going to see, whenever we have something interesting like a harmonic appearing in a biological organism, there's always the question of purpose in a different sense of what's the biological purpose. Like, those things don't just come about by accident. Some bats seem to have more harmonics than others. Well, why might that be? Why might evolution have favored that such that they came about? And to answer that question, we will be seeing that question at the end of class after we've learned and discovered some cool stuff. The next and last question that we're going to answer together is, do baby bats have different signature calls than adult bats? And so, we want to know, what does a little baby sound like? You might remember from earlier in the semester, we were looking at big brown bats and how they can recognize the sex of other bats purely from their echolocation calls, which gives them a useful piece of information when they're maybe trying to find a mate in the dark. It's a super useful thing to be able to do. So can they do that with young? Well, this is a table that shows a review article looking at all sorts of different ways that people have been looking at, can bats distinguish different features of the sounds of other bats? So, for example, can they tell a bat's sex? And these are for different species, and whether the answer was yes or no. And then the age, that's what we're looking at here, is about juvenile versus not juvenile, so we'll look at that. Reproductive state, body size or condition, group, like is this from my colony of Mexican free-tailed bats, or is it a foreign colony? And so they figure that out. And even individual levels. For certain species, can they actually detect and understand whether or not they're seeing their exact friend? Is that Frank the bat, or is that Mary the bat? And you can tell the two of them apart. And so this is a bunch of research has been done. And so let's take a look at sort of that same vein of research. How do they figure this out? And specifically, let's look at the cutest example we can of these very, very tiny baby little brown bats. Now, this particular study was very fortuitous. They found an attic where there was a colony of little brown bats, and they were pregnant, and they decided to hang out and just check on them every night until they finally gave birth. And then when the moms went away to go get food so they could come back and nurse their young, they actually took, for a brief moment, each one of the baby bats in the colony and did some activities with them. They put them on this little suspended ledge here and then pushed the button, and those bats dropped down gently onto a foam pad. All this was approved by an ethics board, and as that bat fell, at first it didn't make much noise. In fact, for the first few days of its life, it didn't make any noise when it fell. But after 4 days, as it flopped down, it continued to just sort of flop down there gently. It made a noise that looks like this. Here, this is the spectrogram of the call, a long signal that cuts across and kind of looks like a bat. After 7 days, it continued to flop down, made a little bit different noise. After 11 days, you can see that the signal's starting to tighten up a little bit. And after 15 days, after 2 weeks, not only did it sort of fall and make this nice little echolocation call, but it also started to flap its wings. 19 days, more flapping, and a call that looked like that. After 24 days, not only did it start flapping, but after you get out here into the 28-day range, it actually was able to do little bits of flight. So that's about how long it takes for a little brown bat to learn to fly. But it also, you can see the evolution of its call from, a babbling baby sound, blah, 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 to an e, to something that sounds a lot like the adult. In fact, really, by the time you get to even 2 weeks in, you start seeing calls that are really similar to what the adult looks like, at least in terms of its characteristic frequency, its angle. And so they're really learning how to speak their echolocation calls pretty quickly. This figure on the left is a graphical view of that exact same data set. It looks like I put a line here about 3 weeks here, that the duration starts off really long, really babbly, and by 3 weeks it looks pretty much identical to what the adult has. And same thing with the lower frequency bound and the upper frequency bound, although these bats are a little bit more scattered and varied in their upper frequency, still trying to control those high sounds, those high notes, or it must be harder to get a control over than the lower ones. And in big brown bats, a different species, there was a study done that had field measurements of adults versus juveniles here, and also a difference in characteristic frequency that is still seen even more than a month into that juvenile's lifetime, and those duration of the call is a little bit longer. And so when they took these bats into a laboratory into really high resolution call recordings and then put them into a computer, the computer was able to tell the difference successfully between the adults and juveniles about 70% of the time, which is not terrible, but 50-50 is random guessing, so it's not great either. And I'm hoping that bats can probably do a lot better than this, and it's less likely that we'd be able to do this in the field, telling the difference between these bats purely based upon their echolocation call. So once they get going into that couple months range there, they really are indistinguishable for our ears from one another, but to each other's ears, they can still tell the difference. Now, one more sound a baby bat makes. Let's go back in time a little bit here, and let's learn about a call that a bat makes before it can even echolocate. Remember those first few days, it just sort of flopped down. But what they do is they have this isolation call, which is essentially just this, as it sounds, when a poor baby bat is isolated, it calls out to its mother saying, come feed me, just like a baby kid does, baby human. And those calls are a little bit unique to that individual. They have a certain pattern so that you can tell your child apart from other children. And so you should see in this picture here, there's this female here labeled ID number 3, so the third bat in the nest. She's after 2 weeks older, you're supposed to be able to look at these and say, I can see the same sort of characteristic patterns in her call. I can recognize her voice. It's still the same voice, even though it's matured a little bit. But I can also tell that this bat is different than this male, this bat number 9 here, which has a different sort of pattern in its calls, which you can see persists from day 1 through day 15. So that the idea is that the mother bat can come back from her night of hunting and come and give milk to her baby, which she identifies both by its isolation call and also probably its smell. Now it's time to get to work here, as we have a mystery. We're trying to solve why is it that sounds get quieter as you get further away, in particular bat calls. And so we're going to be analyzing this data set that we collected a couple of weeks ago when we were outside. We took a little ultrasonic dog bark repeller, which just makes noises at a constant frequency of 25 kilohertz and has harmonics at 50, 75, and 100 kilohertz. And then we walked away from the microphone, pushing the button periodically so that we would see how that signal got weaker and weaker and weaker. And we want to understand what exactly is going on there. We learned last time about something called geometric spreading, where the energy is spreading out over a larger and larger surface area as we spread out. And so that explains one of the reasons why the energy gets lower. And so we wanted to check and see. We made a graph of this. And so what I'd like you to do now is get out your graphs and let's look at what patterns we notice. Your graph might look like this one here, where we plot the geometric spreading theory, which is where we lose energy because the energy is spreading out over a larger surface area. That's the green curve here. But if you take a look at our data, which is these blue dots from the 25 kilohertz signal, it does not fit on that curve very well at all. And in fact, remember, this is a log scale. So this is actually decibels here on the left side. And we are looking at something like 30 dB of difference between the model and the theory. That's a huge difference. And so we need to understand what's going on there. To do that, we need to understand what sound is. Remember that sound is the systematic motions of the air. And so let's take a look at that. These little black dots represent individual air molecules, and I've colored a few of them red, or actually Dan Russell did. I colored a few of these red here, shaking back and forth, so that we can notice that even though the energy is moving across the screen here, it actually happens because the molecules move a little bit until they run into their neighbor and collide and transfer the energy onto the next molecule, and then they bounce back to where they came from. So that's what sound is. It's pressure moving these molecules forward and back in this systematic sense. But there's something that's missing from this figure that's kind of hinted at, which is that each of these little molecules here is actually moving randomly, normally, even when there's no sound in there. And that's hinted at because of the random placement of these molecules. But maybe a better way to look at that would be to look at this picture here, showing that these molecules are moving around, vibrating and moving randomly and crashing into each other, just sitting there until the sound comes along and makes them move in a systematic pattern in addition to their random motion. That random motion is called the thermal energy that those molecules have. And so warmer air has more motion and more random motion to it, and colder air has less motion. So let's take a look a little bit at that random motion. So here we are, if we imagine water molecules in a container. And each one of these little things right here represents an individual water molecule. You can see the 2 hydrogens and 1 oxygen, H2O. And what I want you to notice is all the ways the molecules move randomly. So let's go ahead and watch that again. And you can see that they are spinning, some of them. That's rotational motion. That's energy. There's vibration. You can look at those molecules pulsing in and out. Or you can look at the hydrogens pulsing in and out there. That's vibrational energy. And of course, the translational motion, that's the word we use to describe them moving from one place to another. And so there's all these random motions that happen. And what we're thinking about when we think about sound moving through the air is that sound's systematic movement can get turned into the random movement of heat. So let's say this little red particle right here represents an individual molecule of air, and it gets hit in just a certain way such that in addition to moving along and sending its energy across the screen here, it also starts rotating a little bit. And that's energy that would have gone to the sound that's now lost as the random rotation of that air molecule. And so we have this systematic movement turning into heat little by little as it moves along. And that's a process that we give the name attenuation. It's just a simple word to describe that we're losing the energy to heat. Sound getting converted to heat. Now, does this happen to all sounds? If we go back to our curve here, the blue dots on here were the geometric spreading plus attenuation for the 25 kilohertz signal. I've also plotted on here, though, the first harmonic, these blue triangles. And those blue triangles, they follow a curve kind of like the other one, but look how much steeper the slope is right at the beginning. They seem to be dying off at a faster rate. So if I ask the question, do all frequencies of sound suffer equal attenuation? Why or why not? And so we have to think about which dies off quicker. Are low frequencies dying off quicker? Are high frequencies dying off quicker? Or are they the same? And the answer when we actually go about plotting this is that there is a very clear pattern. Let's take a look at this here. This is a graph showing frequencies in kilohertz, and then the dB of absorption from attenuation for every meter that the signal travels through. And there's a couple different constituents that go into making up the attenuation, a couple different processes. Remember, there's the rotational motion, the vibrational motion, all sorts of things like that. And so those all add up to this big black curve. And so let's focus in on the area where bats work. Now remember, bats start at around 20 kilohertz or so, a little bit above 20, and they go up to a little bit above 100. So if we look at where those are, that's if you're at 20 kilohertz, you're losing about 1 dB of absorption per meter. Remember that you lose half of your signal for 6 dB. So it will take 6 meters for this signal to get cut in half. At the 100 kilohertz range, now we're losing 1, 2, 3 dB per meter, and so it really only takes 2 meters before that signal will cut in half, and then it keeps going. It's going to cut in half again and again and again. It's going to die off very quickly. So you're getting 1 to 4 dB of loss per meter for bat frequencies, but it's much higher at higher frequencies. Higher frequencies attenuate faster. And that is a really key discovery that we've made. And it has to do, of course, with the fact that the molecules are moving back and forth more quickly. They're bouncing back and forth more quickly in a higher frequency. So it's not surprising that there's going to be more collisions that are happening more often. And so you're going to be losing your energy more rapidly. But let's see what this means for bats. Higher frequencies attenuate faster is a feature of physics and the physics of sound waves, but it has a huge implication for bats. We had another question that we asked a long time ago at the beginning of the semester. Why do calls always go from high to low instead of from low to high? What would make the difference? And we, I think, can finally answer that. So it really has to do with this question of how do you recognize the end of your call? A typical call starts high and ends low. So when you emit, you have this, and then when it gets returned, which frequencies get attenuated more? The high frequencies get lost more. And so it's sort of your return to echo kind of comes back in, and then ends with a triumphant ending. And you're listening carefully until all of a sudden you say, I heard the end of my call. I'm sure I heard the end. I can stop listening now. If it was the opposite way, if these calls started low and ended high, you'd have this echo where, first of all, it would come back suddenly, and you may or may not be ready for it, and it'd be very loud at the beginning, and then you'd be listening and listening and listening, wondering, is it done yet? Did I lose it? I'm not sure if I've heard the end of my call yet. And I think that confusion about where the call ends, or the clarity about where it ends, could be what makes it just a little bit easier for the bat. And so what that means is that knowing when the call is over might allow the bat to relax for a bit at the end of the call. Keeping those neurons sort of charged up and ready to receive signals, that takes energy. They have to keep themselves ready to listen. And you know this from your own personal experience, that if you're tired, you have to really focus in on listening and devote some energy to it. And so anytime that you can conserve energy is all the better. And so what might be happening, this is purely speculation on my part, you make the call and you listen carefully until the call ends, and then as soon as it ends, you can be sure that it's time to relax until you're ready to make your next call. And that cuts out a little bit of the duty cycle of doing the sounds. And so I think that this could be an explanation, and it certainly fits with the physics of sound that we've learned, that the higher frequencies get lost more quickly. You're more likely to get those lower frequencies back because they're less likely to attenuate, and that means you'll know when the call ends more clearly. So let's take a look at a question that people asked way back in the beginning of the semester. They said, if bats are widely known to emit high frequencies to aid in socialization and echolocation, why might they sometimes emit frequencies that are detectable to our ears? Why do they sometimes give off low frequencies? And so, well, social calls are lower frequencies than the echolocation calls usually. That's, if you take a look at here, we're looking at sample echolocation calls from 3 different species, and then a variety of different social calls. And if you look at all of these situations, in almost all of them, the social calls go down to lower frequencies than the original echolocation call. And that's kind of weird. Why would that be? Well, while we're talking about social calls, we're going to take kind of a little bit of a diversion, but it might help us understand things a little bit. And we're going to listen to Sid's song. To give us some extra context, let's meet Sid and learn about the sounds that Sid makes that are social calls.
This is our buddy Sid here. Sid is hanging from this pouch, and the ladies, the females, are in this pouch, and these guys, they start to call, but as they start to sing, it's like birds in many ways. I mean, it's truly song in the sense that what they're trying to do is both defend their territories and attract mates. So here he is, he's hanging, and he's got the gland on it, he rubs himself on it, and he's going to flap his wings and send this perfume over to the ladies, and he's going to woo them. And he's going to woo them with this courtship song. And here is Sid in all of his glory, wooing the ladies.
So it's so cool to hear Sid and other bats making these social calls that often go into lower frequency ranges. And in fact, I was super thrilled because a couple of days ago at the duck pond, when we were recording as part of our usual class observations, we caught the Mexican freetail's song on tape here. And this is the sonogram of what it looks like. And I don't know if you can notice, they divide some of the different sounds that they make into different things like chirp, buzz, and trills. And maybe you can recognize some of those trills there, some of the chirp, some of the buzz. And those are all arranged according to what people have noticed and observed about them. There seems to be a specific grammar or order that they always combine them in to give them particular meaning. And so I want to just play this song in all its glory, the one that we recorded here on the CSUN campus. Well, what beautiful songs they make. And all these other amazing different looking sonograms with different sounds that they're using for social purposes that do indeed go to lower frequencies. Which brings us full circle back to our question, why? Why are they going low with their social calls? And if you think about it, well, if you want to send a signal to a neighbor, you want them to be able to hear it. So you're going to want to choose the frequency that's the most likely to penetrate a far enough distance for your friend or neighbor to hear you. And so you're going to go down to a lower frequency because higher frequencies attenuate faster, and the higher frequencies are going to die off. And so they're really good for echolocating, where you just want to see what's right around you. But if you want to if you want to fly along and hunt near your friend, you can communicate with each other over those lower frequencies. And then echolocate only at the higher frequencies, and then you each have your own little space of high frequency sounds that are bouncing back to you, but they die off before they get towards your neighbor, so they don't interfere with your neighbor's hunting as much. But you can still talk to your neighbor very easily by using those lower frequency sounds. And so same thing with distress calls. If you wanted to make a distress call, you want it to get out to as many people as possible. And so those bat distress calls go lowest of all because those signals get sent out and they travel farther because higher frequencies attenuate faster. And that's the main message that we want to end with for today.